Alright, welcome to page 2. So here we're starting out with a request to figure out which of these chemical equations represents oxidation and reduction. Again, we'll recall that oxidation is the loss of electron. Leo, the loss of electrons is oxidation. This means that the oxidation number is going to increase. And the gain of electrons is reduction. It's called reduction because the oxidation number goes down. So in order to have a oxidation-reduction reaction, we have to have a change in the oxidation number from the species on the reactant side to the species on the product side. So what we have to do is use our knowledge and our reference tables to assign oxidation numbers to all of these species. Looking at multiple choice selection 1, we see that we're starting with silver nitrate. Now, silver nitrate is an interesting problem because it is not what we call binary. It has more than 2 atoms. We have 1, 2, 3 elements. So that means we're going to have to refer to reference table E in addition to our periodic table to find the oxidation numbers of all of its components. So looking at table E, the table of selected polyatomic ions, we find that the part in silver nitrate that is here is actually the nitrate, which has a charge of -1. So since it's a polyatomic ion, it has 4 atoms. Collectively, these 4 atoms work as a group to have a charge of -1. So what I'll do is I'll place this in parentheses and we'll put its oxidation number above, -1. When we look at the equation, we again find nitrate on the product side. So while we're at it, we'll put it in parentheses and put its charge, -1, above. Now we have to find the oxidation states of all the atoms in the compounds listed. So the rest of the atoms will be found here on the reference table, on our periodic table. So silver has only 1 listed oxidation number. So silver has a oxidation number of +1. Potassium, again, only has 1 oxidation number, +1. And iodine has many oxidation numbers, as you can see here. But since the sum of the oxidation numbers must equal 0, we only have 1 potassium and 1 iodine. Iodine must be -1. Again, silver is +1. And for the same reason, iodine is -1. So when we look at the atoms on the reactant side and compare them to the product side, we'll see that silver has an oxidation state of +1 on the reactant side, +1 on the product side. There's no change. Nitrate doesn't change, potassium's not changing, nor is iodine. So this reaction is not a oxidation-reduction reaction. This reaction is actually a redox reaction. In a redox reaction, what we have is we have 2 ionic compounds whose ions switch places. So the outside ions will join together while the inside ions will join together, which is exactly what we see. This double replacement reaction and all double replacement reactions are never redox reactions. Oxidation numbers do not change in double replacement reactions. Let's look at the next equation. In this next equation, again, we have silver nitrate. So we know that nitrate is going to have an oxidation state of -1, And we have nitrate on both sides of the equation. Now, since we had silver nitrate in the previous equation, we also know that silver is +1. Now we have to find the oxidation states of the remaining elements. When we look at copper here, and we find it on our reference table, we see that it could have an oxidation state of +1 or +2. But we also notice that this copper is a lone element. It is by itself, and we know that since the sum of the oxidation states is 0, there's only 1 element. It must have an oxidation state of 0. Now when we get to copper nitrate, we'll see that we already know that the nitrate has an oxidation state of -2. But copper could be +1 or +2. So we'll assign the copper an oxidation state of X. Now we notice that we only have one copper ion. So what we're going to do is we're going to circle the oxidation numbers and the subscripts in a vertical fashion to help us create our mathematical equation. We know that in a compound, the sum of the oxidation numbers is always 0. So our mathematical formula ends up being x times 1 plus -1 times 2. Notice that for this nitrate, I'm only taking the subscript for the entire nitrate, and we do not ever manipulate the subscripts in a polyatomic ion or use them. So this mathematical equation must equal 0. So we get that x minus 2 has to equal 0. So that means the copper must have an oxidation state of +2. And lastly, when we get to the silver on the product side, we see that it is by itself. And we'll recall, any lone element always has an oxidation state of 0. So when we look here, copper had an oxidation state on the reactant side of 0, and on the product side is +2. 0 to +2 is an increase in oxidation number, so copper was oxidized, while silver went from +1 to 0. That was a reduction in oxidation number, so silver is reduced. So this is our oxidation reduction reaction. Let's look at the next two choices and figure out why they are not examples of oxidation reduction. In choice 3, we'll notice that this is an acid-base reduction. We begin with the acid, sulfuric acid, found on reference table K, and the base, potassium hydroxide, and they form the salt, potassium sulfate, and water. Recall that we can write water as HOH. So again, we have a double replacement reaction where we have the ions simply switching places. So the outside ions, the potassium sulfate, come together, and the inside ions, H and OH, which is the same thing as water, come together. Number 4 is also an acid-base reaction. And again, we have the ions going and switching places where the outside ions, barium chloride, come together to form the salt, and hydrogen and hydroxide come together to form water. Acid and base reactions are a special kind of double replacement reactions, and recall, double replacement reactions are never redox.